I'm Sarang. The agenda for this module is to analyze the challenges in existing computing methods and what are the probable solutions and how RDD attempts to address some of those problems. Followed by that, we'll understand what exactly is an RDD, what are the functions, transformations, and actions available on an RDD. We will go through the process of understanding how to load data and save data through RDDs, and whether RDDs can deal with data that comes in the form of key value pairs, essentially JSON in this case. What are the different types of RDD options that deal with JSON data or with plain text data, or how do we convert text data to a key value pair and key value pair back to a text data? So we'll go through all those operations. And as part of the same discussion, we'll touch upon RDD lineage and persistence. Lineage will help us understand how an RDD intelligently tries to keep track on the number of steps that it has completed on a particular piece of data on a given worker node, so that if there is a failure, it knows what process it has to follow to make that data available quickly and catch up with other RDDs that working well on a similar data set on different worker nodes. And how RDDs can be persisted, so that if you have to reuse some of the operations in the Spark without reloading the data again, right? Persistence and caching comes to our rescue. So we'll touch upon those concepts. So to begin with, what are some of the challenges in existing computing methods that led us to learn all these big data tools and also led to the evolvement of these kind of analytical tools? So when it comes to iterative distributed computing, three important terms: iterative because processes are repeatable, distributed because if they are repeatable, they can probably be run on different machines and each one utilizing the resources available on that machine. And all that is now holistically made available in the form of a big data cluster. So iterative distributed computing, that is processing data over multiple jobs and computations. We need to reuse or share data among multiple jobs. So there are problems with the current computing method, that is MapReduce. And since we are discussing Spark, so we are discussing the problems that were there in doing all data processing on Hadoop appliances earlier. One step before that, to understand how difficult it was to process data. But then, since we are at an advanced stage, we'll look at some of the challenges in Hadoop. We need to store data, first of all, in an intermediate stable distributed storage such as the HDFS. Multiple IO operations make the overall computations of the job slower, and replications and serializations make the process much more slower. On MapReduce, jobs require all data to be made available in HDFS for them to refer that data. Now imagine if you were to set up a big data cluster and write MapReduce jobs to run on cloud, then that requires all of data to be made available in the cluster's HDFS and not on cloud storage. And then that becomes a very painful process wherein you will have client data showing up in cloud buckets, and then you have to move that around to HDFS. HDFS, whenever we save data, it goes down to some form of physical storage. Since HDFS is distributed, we don't see that as a limitation, but if you keep on saving terabytes of data every day or every few hours, there will be a time wherein HDFS is also going to get full. So you need to keep moving data around. You can maintain high volumes on HDFS, but again, that requires some form of data movement. So that's a painful process, first of all. Second, when the data is made available in HDFS, it has to be loaded in memory eventually for those jobs to be run. If you have multiple steps in the MapReduce job wherein you standardize all the names in the data set, and by standardization we mean, so if a name is all in lowercase, we say make the first letter of all words in the name as capital letter. So if you have name as Steve Jobs, S and J of Steve and Jobs respectively has to be capitalized. There could be names that come in a consistent format, but to make sure you have data all available in consistent format, you do this transformation. Similarly, you have another transformation that says the date of birth of an employee is mentioned. Subtract that from today's date to arrive at the age of the employee. So you could have large number of transformations specified to be run on a job. So if all of this were to run in Hadoop using MapReduce programs, the way it used to work was load data from HDFS into memory, transform name from lowercase to uppercase, and then again write that intermediary data to some temporary location in HDFS for that to be picked by the next stage that will say, okay, now I have name modified. let me operate on date of birth and come up with a new column called age. Again, that will be written back to some temporary storage once again for that to be loaded by the job. So even though this was far better than the previous approaches we had as compared to the periods when we did not have big data tools available, right? So Hadoop did improve a lot of that process, especially in terms of data management. But then again, there were latencies involved in IO operations, and that made jobs slower. And that is the reason we could not perform real-time analytics using Hadoop. And part of that also led to evolvement of tools like Spark, Taze, Storm that specialize in real-time data processing. So Spark overcomes this by not writing intermediary data to HDFS, but rather it considers all set of operations as a pipeline, and once the pipeline is defined, it runs data through that pipeline at once without generating intermediary output for that to be picked up by subsequent stages in the process. And lastly, many times when we are dealing with data, we can either use Java, Scala, or Python to interact with these tools. And when we do that, each of these programming languages have certain native data types, like Python has lists and dictionaries as its own internal data types, right? As opposed to that, Java has array, an equivalent of list, and hash maps as equivalent of dictionaries. And they could be something similar in Scala. So sometimes we want to save these objects or this kind of a data representation like key value pair or list of values to a native programming object, because we know that if we save dictionary as a dictionary object, then Python programs will require at least some lesser time in loading dictionaries back as opposed to reading a string that has to be again converted back to a dictionary. So then there comes the concept of serializing and deserializing the objects that again further make this process slightly time taking. So all of that was done by Hadoop, and that was partly because it had to generate data after every stage of processing, and that data was picked up by subsequent stages until the entire process has completed and it has to return with the final output. So some of that was actually overcome by Spark. So probable solution to many of these problems was to reduce the number of IO operations through HDFS, and that is why we started processing data in memory. This can only be achieved through in-memory data sharing, and in-memory data sharing is at least 10 times faster and up to 100 times faster than network or disk data sharing. So if we look at the diagram below, we could say we have input coming in from an RDBMS or from a text file. We have iteration 1. So the diagram on top is about the Hadoop processing pipeline, wherein you have iteration 1, let's say converting name, and then all the green chips that we see here, they are actually the intermediary data that is generated by iteration 1, converting name to uppercase or initial letters to uppercase. Then that gets picked up by iteration 2. So iteration 2 takes this as output so that it does not lose any of the previous iterations output. In addition to that, it will transform or it will convert date of birth to an age column. And then there could be similar other iterations that you would perform. After every iteration, data is generated. It is written back to HDFS and loaded back in memory, involving a lot of IO operations. As opposed to that, the diagram below does a one-time processing wherein you define iterations all at once, iteration 1, iteration 2, and 3. And we have just defined. This is equivalent to saying we have written a define function in Python, but we have not executed that function. Okay, just the definition. Once the definition is available for all the transformations that we want to perform, we say start reading data, and it will load all of that data in memory, and that data will be run through all of these iterations at once in parallel, so that iteration 1 is performed, iteration 2 is performed, and all of that is combined together to come up with one final output that has the result of all these iterations put together. So first is it does a distributed processing between the steps. Second, it does not have to load and unload data to HDFS. Third, temporary data is not generated, so HDFS always remains cleaned up. So there are a lot of benefits in using Spark over Hadoop, and that is why you would not hear anyone using Hadoop these days as long as they do not have any complex jobs written in the past in Hadoop that they don't want to again risk converting to Spark. So that's the only reason some organizations would be using Hadoop. So some of these efficiencies that are made available by Spark, they are offered to us in the form of an object called an RDD. So RDDs are the perfect solution to all the problems that we have just seen in Hadoop, as they try to solve these problems by enabling fault tolerant distributed in-memory computations. So earlier, when Hadoop was not in place, the first thing that developers of Hadoop had in mind was to have a distributed data storage so that data can be saved at one place in HDFS and can be referred by multiple executors in some form of block, so that every executor works on that data individually. Now, coming to the block concept, if you had a file of 1 gigabyte and if you have the block size of 128 MB, then that file will be split into 8 blocks, and every block will be executed on a different worker node. Every block will also be replicated on a different worker node HDFS to make sure it was fault tolerant. That means if one of the worker nodes hosting a block goes down, there will be another worker node saying, I have the copy of this data that is lost on that machine and you may process this data, right? So all that was made available over HDFS. But now if we don't want to refer HDFS and do everything in memory, right, then we want to replicate the same model in memory, so that if one of the worker nodes in Spark goes down, and let's say it was having a 1 terabyte RAM and you have a 100 node cluster, so it will be 100 terabytes of RAM. So the copy of the data that was there on worker node 1 should have a replication on, let's say, worker node 10 or worker node 20, so that if worker node 1 goes down, either 10 or 20 can be referred to process the same data. Now this data is not available in HDFS, it is loaded in the memory. Memory of 100 systems is combined together to have one massive memory, and that we call as a distributed in-memory location. And that distributed in-memory location is again fault tolerant, so that if you have 1 gigabit of file saved to this memory, it will again be split into 128 megabytes of blocks. So 8 blocks essentially. 8 blocks will be saved on different worker nodes, and the copy of all these 8 blocks will be saved to other worker nodes, so that if one of the worker node goes down, it knows what other worker node memory it has to refer to process that data. So RDDs do all of this internally automatically. We don't have to specify any of these properties explicitly for RDDs to operate on this. But we should know the model that makes RDDs work on this data, so that we are able to write these operations in a better way and understand in what scenarios caching will be required. How do we share variables across different RDDs? So when everything works in a distributed mode, there comes a complication of having a global variable that can keep track of the number of records that were processed, number of records that were failed. So you need a global counter. So we will come across those kind of variables as well that are made available by RDDs. So since RDDs are created over a set of transformations, it will log all those transformations rather than the actual data. So you will have a transformation in this form wherein you will filter the data, you will transform the data using map operation, and you will also combine few RDDs using join operations. In case we lose any partition of RDD, we can replay the transformation on that partition in lineage to achieve the same computation rather than doing data replication across multiple nodes. So this characteristic is the biggest benefit of RDD. It saves us a lot of effort in data management and replication, and also achieves faster computation. What is an RDD? RDD stands for Resilient Distributed Dataset, and it is a distributed memory abstraction that lets programmers perform in-memory computations on large clusters in a fault-tolerant manner. Now, there are many important terms as part of this definition, and let me unpack some of the details related to it. So as I mentioned in the last session as well, that as compared to the Hadoop programming model, wherein HDFS played a very salient role in making everything available in a distributed node, when we put data on HDFS, that's accessible to all workers that need to operate on it. And then that data is divided into blocks. Those blocks again are distributed on different nodes to ensure fault tolerance. However, when we say Spark follows a similar model, but it does everything in memory, that means when memory of multiple systems forming the cluster is combined together to make or to form a giant memory for processing, that memory again has to ensure that there is fault tolerance embedded in it. That means when a file is loaded in memory, it is again loaded in the form of multiple blocks. Those blocks are loaded from their respective systems. It could be from a file on HDFS, or it could be from a stream from which the data is pulled. Once those blocks are loaded in memory, because this memory is a combination of multiple machines' memory, the blocks are again distributed. So if you have block 1 on memory of system 1, then the replication or the replicated copy of that block could be on the memory location of, let's say, system 10. So that ensures, first of all, it's a distributed memory abstraction. Secondly, once the data is made available in this form, we can perform in-memory computations because it has been loaded in memory. And it is fault tolerant as well because it is distributed across the memory of different systems put together. The good part is it might sound very complex to perform this kind of operation and how to ensure that the data has a replicated copy, it is loaded in memory, and all these features are made available in the programming model. We don't have to implement anything of this manually because all this is made available to us in the form of an RDD, which is an object exposed by Spark. So RDDs again are read-only collection of objects. That means once a data is loaded into an RDD, we cannot add more data to an RDD, or we can definitely filter it out, restrict it to a specific set of records, but we cannot delete few records from RDD or add more records to it. So it's an read-only collection. So first time the data that gets loaded, that becomes the original definition of the RDD. They are the read-only collection of objects partitioned across set of machines that can be rebuilt if a partition is wrong. So there is a concept of preemptive calculation that comes into picture when talking of RDDs. That essentially means if you are dealing with a file of size 1 gig and the block size is 128 MB, resulting in 8 blocks to be processed. Out of these 8 blocks that are being run through a process, let's say 7 blocks are progressing at a regular speed, wherein let's also say the speed of processing those 7 blocks is 10 seconds. And you have 20 steps written in your pipeline to be run through these 8 blocks of data. While the process is running, there is a mechanism that keeps track of the time taken by all these individual blocks when going over the processes that we have defined. So let's say 7 blocks out of 8 have roughly taken 5 seconds to run through 10 processes, and 10 is still remain to be completed. However, there is one block that has taken 5 seconds to complete only 2 steps in the process, and there are 18 remaining to be completed. So then in that case, Spark does an preemptive processing of data wherein it identifies that this block is lagging behind other blocks in terms of completing that operation, and it automatically starts reprocessing that, or again distributes the workload to different workers available in the cluster to see if that can be processed at a regular speed in comparison to the other blocks, so that at the end of the process it does not have to wait for one block to return the result while others have already completed. So that again is an intrinsic feature of RDDs, and it's automatically implemented in RDDs. We don't have to explicitly call that feature. RDDs can be created from multiple data sources. You could build a Python collection like list and pass list of values for RDDs as the input. You could load data from a regular file on your local file system. You could refer a file on HDFS. You could refer a file on Cloud Bucket like Amazon S3 or Google Cloud Storage, or it could be any other table like HBase as well. So there are several options from which data can be loaded into an RDD. And in future, we'll also see when we learn the concept of streaming in Spark, how data can also be streamed from directories which at the moment might not have any data. You start your job and say point those jobs to a specific directory, and as and when the data flows in, the job becomes active, consumes that data, splits it into blocks, processes it, and writes the output to any of the desired data store that you wish to configure. So it is extremely important to get familiar with RDD operations because this is one of the most powerful objects that has all the features of a Spark embedded in it. So there are three types of broad operations that can be performed on RDDs: transformations, actions, and functions. I often refer functions at last because those are like the built-in functions available in Spark. But in addition to that, most of the times when you have to process data or do big data analysis, you start with transformations. Identify what kind of process you need to define in converting your data from one format to other and filtering it, creating new columns in the data set. So once you are done with all those operations, then you will decide how do you want to aggregate your data or to filter it down to a level that you want to reduce it to another data set for further processing. And then lastly, you might also explore the option of invoking any PySpark SQL function on those data sets, like doing a regular expression, right? So one option is you use Python regular expression for filtering your data sets matching a certain pattern, or you could use regular expression functions that are part of the PySpark SQL library. So regular expression is just one example here. There are several other functions like the ones related to date. You might want to convert a date to only a year so that you can do a year-based rollup or a month-based rollup on a data set. So we'll explore all those functions as well in detail. Now moving on to the features of RDDs. So what are some of the features of RDDs? First of all, they have an provision of in-memory computation. All operations are lazily evaluated. That means all transformations are lazy. It does not compute their results right away. That means when you say I'm dealing with employee data set and against every employee I have name as first name, middle name, and last name. But then I'm more interested in having, let's say, the full name of the person. And I come up with a formula that first name is space, middle name is space, last name is the full name of the employee. So I can write this in the form of a transformation, but when I write this, it does not apply directly on the data set. That means I've just defined the operation. Very much similar to saying that I have written a function in Python, but I haven't executed that function yet. So all the transformations that we write in a Spark, they're just the definitions. They don't get invoked automatically until the time when we say now we want to aggregate the data or we want to see the results using functions like collect, that means show me the output, or take, show me few sample outputs. Only then all these operations become active and they are run through the data set and that we wish to process. Fault tolerance, RDDs track data lineage information to rebuild lost data automatically. I did mention about this. So first of all, there is a case of one worker going out of the cluster, failing for one or the other reason. So then in that case, the block that was supported on that worker will automatically be switched either to one of the existing workers or to a new worker to process that. So RDDs internally keep track of what data is being processed on which worker, and if there is a failure on a given worker, they spin up a new process to make that data available. Secondly, it also keeps track of the steps that data has to go through. So we'll also touch upon the concept of checkpointing. That is a feature in Spark wherein if you have a lot of steps to be performed on data, you could also say checkpoint my data at a given point in time. So that means if you are performing, let's say 50 steps of transformations, your RDD was already through 30 steps and at that point in time it failed on one of the blocks. So one option is you get started right from step one and say, I'll again go through all 30 and remaining steps for that data to be available. The other option is after every 5 steps, I say checkpoint. That means I'm creating a restore point for my RDD. And that would imply if it had failed at, let's say, step 32, so it would have been checkpointed at until step 30. And then in that case, any worker that will have to restart the computation on that data set or that block of data, it will not start from step 1. It will start from step 30 because the results until step 30 would have been stored somewhere on HDFS or in memory while that data was getting processed. So that again is a very good feature of RDDs, but applicable only in streaming context when data keeps flowing in the form of streams. RDDs support immutability. Data can be created or retrieved anytime. They support partitioning. Partitioning is the fundamental unit of parallelism in Spark RDD. So if you think of any big data appliance, always keep in mind why are we using big data? And the basic premise behind that is distributed computing, applying parallelism when it comes to processing data. So partitioning and parallelism are often the fundamental units of any data structure you would interact with in the big data space. Users can reuse RDDs and choose a storage strategy for them. Now, as and when we progress on different operations in RDDs, if we are not caching RDDs, we cannot reuse them. That means if you have written a bunch of transformations and then you aggregated the RDD, don't expect the initial version of RDD to be again available in the form of the variable on which you have written all these operations. That means if you want to perform two aggregations on the same data set, that would imply you will have to have either two RDDs created on the same data set, but that is not logical because you'll be burning resources in the memory to cache that much data. To avoid that, not to cache, but rather spin up a new RDD. To avoid that, we cache RDDs. That means once we create an RDD, it remains in memory for that to be reused for any subsequent aggregations that we want to perform on the same data set. So that is made available in the form of persistence. And then the operations that we write on RDDs, they apply to all elements in the data sets through map or filter operation. So there is no way that even a single record in the RDD can skip any one of these operations. So all elements, all records in RDDs have to go through all steps that we define process in the form of transformations, actions, and functions on RDDs. Thank you once again.